Hi. So yeah, I'm going to talk about memory allocation in Go in a broad sense. So how the program itself allocates memory, how stuff go into memory and stuff like that. Before I go into it, who has before Go, who had experience with allocating memory and freeing memory and doing this stuff? Wow, a lot of people. Okay, but not everyone. I'd say it's about 60-40. So one of the reasons I was motivated to do this talk is in the community we have a lot of people that come from languages like Ruby, like Python, people like myself that only saw this stuff in the computer science courses in university, and I thought it was a lot of fun rediscovering it with Go, and I thought it was really interesting, especially how Go does it, so I wanted to share. I hope you'll find it interesting. So this is what I'm going to go over. At first, I'm going to talk about the program memory model, so how the program exists in memory, basically, where the variables live, where the pointers live, etc. Then I'm going to talk about allocation and garbage collection. Hopefully I can make you think a little more about things we do every day with Go. And finally, I'll just touch a little bit on how to monitor memory use. So that's kind of a hard problem, I think. It's not always straightforward, so I hope I'll give you a few ideas on how to do that. So yeah, let's start with the memory model. So this is like the classical memory model. Most programming languages and runtimes use that. So you have basically 3 sections in memory. You have the green one, the blue one, the red one. I color-coded them. I probably didn't put the names everywhere, so I hope no one's colorblind. So yeah, so you have constants and instruction, stack, and the heap. I'm going to give you a bit more detail about those. So the first one, the constant and the code. So basically where the instructions live, where the constants, the global variables. Not very excited. It's all static content. It's usually small. It's determined at compile time. Not a lot exciting happening there. So it's just sits in memory and get accessed by the program to just know what to do, basically. Then we have the heap. So the heap has an elastic capacity. What that means is as the program needs more memory, we can request more memory from the system. It is, by that fact, limited by the system. So if you go through all your RAM and your swap, basically you'll run out of memory at some point. But it is kind of like our main source of memory resources. That's what holds all of the pointers, the array, the data structures that you have in your code. So really, all the memory heavy lifting is happening in the heap. Small caveat here for anyone who paid attention in computer science class. Heap is not actually a heap data structure. It's just not. So yeah. And the one I found more interesting, because some stuff happens in it, is the stack. So it represents the state of execution. So when you print a stack trace, you know where you are in your code. So it's composed of stacked frames. What that means, I'll go into more details in a minute. But every frame basically holds the function that is being executed and its local variables. So I'll give you a little example. We'll have the stack on the right and the code on the left, and like the arrow will show you roughly where we are in the code. So I have some code here. It's very bad code. It's just for demonstration purposes. Don't do that. That's just stupid. So you have the main function that is getting a result from the level A function, that is getting a result from the level 2 function, that's just returning like a sum of 3 integers. So when we're at main, like the stack has one frame, because there's just one function that's been called. It's the entry point of the program. And it holds the variable A, B, result, and println. After that, so we call level 1, the function level 1, and what happens is we get another frame on the stack. So it goes up like a stack. That holds its local variables, C, D, and E, with the values, and that calls level 2, that stacks up again and does holds its own local variables. So you can see here that we have the same basically values a few times in our memory. And then when level 2 is finished, it's returning to level 1, so we remove it from the stack, and then it returns to main, so we take it off the stack as well. So this is kind of how the stack works. So basically, every time we call a function, we add something on the stack. Every time the function returns, we go, we remove it from the stack. So there's a few things that don't really work here wouldn't really work here for the current model of Go, in my opinion. First of all, we have that model was obviously single thread execution. You have one stack, you have one execution state. Not very good at concurrency, basically. And stacks in most runtimes, programming languages, systems, they had a predefined capacity. So you'd get 1 or 8 megabytes, for example, of stack. And if you call too many functions, if you go too deep, you basically get a stack overflow. You run out of the memory just on the stack. Not on the system, you'll still have might still have plenty of RAM, but your stack is full and you get stack overflow. So that's might be a problem as well. And if you want to do concurrency well, you'd have to, if I go back to the model, so you'd have to basically take all of those and have multiple instances of them. And obviously, you'd have the constants in the instruction duplicated, and you'd have a heap that won't be shared, so sharing information is a problem. As you can see, that's not what Go is doing, right? So hopefully I can show you what Go came up with. So in Go, we have, when you run a Go program, there's one heap. There's one place with the code and the constants. And then you have one stack per Go routine. So every Go routine will have a stack attached to it, basically. And they also made it elastic. So the stacks are basically borrowing memory from the heap and putting it back on the heap when they're done. So that's pretty clever solution, I thought. So this is more what it looks like. So since the stacks don't have a predefined size, they can be very, very small, which lets us have a huge amount of Go routines with very low memory footprint. So the stacks can be very small in size, and they can grow much larger than, they don't really have a limitation here. Okay, so hopefully that was kind of just introduction, how memory allocation works for the program. Now I'm going to talk about how we do it in code and how it relates to that, basically. So we have structs, right? So an object with a few things inside, just a data structure. And we have two ways of initializing them. So raise of hands, who uses the solution on the right? Wow, 4. Okay. Who uses the solution on the left? Okay, yeah, that's what I thought. Yeah, I also prefer the solution on the left, mostly because you can initialize values here. But really what's happening is the real difference is that when you do new, you instruct the Go program to create the data structure on the heap and give you a reference to it. Whereas when you do end the struct with curly braces, what happens is you create a local variable of the struct, and then you request its address. Now that in languages like C would be a terrible mistake, because as soon as that function that does that goes off of the stack, the local variable will be lost. But in Go, it's implemented as when you request an address of a local variable, it actually creates a new instance on the heap. And it's basically equivalent to new. So I prefer this approach. I think it's more scalable, and it's nicer when you do need to initialize the attributes. Then you have arrays. Nothing too crazy there. So if you have an array with 10 items, you can say, I have 10 strings, I want to put them in an array. Now, if you're too lazy to count the number of things you have in your array, you can just put ... Apparently not everyone knows that. It's quite neat. I like that. I use that a lot. Yeah, and that creates an array for you. Arrays are immutable, so you cannot really change them. You would create a copy if you change them. And then you have slices, which are kind of like the lists that we use in Go more consistently. They are the things that really let us do what we need. But they can be a bit tricky sometimes, especially in terms of memory allocation, because first of all, they require an underlying array. So a slice is nothing more than a pointer to an array and a capacity. So when we do make a slice of strings and we pass it length and a capacity, what it does is creates an array of length capacity and creates a pointer to this array that says I'm pointing to the first few elements of length len here. So it's basically the same as doing what I did just before. So here I had my Coachella best acts array, and if I get just the top 3 elements, I will get a slice of this array, and this array will point to this slice will point to my array, my previous array. Now, the problem with that is if I change stuff on my slice, so if I take my slice variable and I change stuff, it will change the underlying array. So that could be quite weird. Also, you can see that here we use make, and for structs we use new. The real difference here is that new just allocates the memory for you and sets it to 0, whereas make actually does an initialization. So for example, for slices, make will create an underlying array, whereas when you do new, you don't create anything. You just take a piece of memory, set it to 0, and get an address back. So that's kind of like the difference between make and new. Now, yeah, so you can have like pretty weird stuff with slices. For example, if I have an array of 5 integers, I do a slice to the first 2, and I append something to this slice. It will actually put the item in the underlying array. So if I'm still trying to access array, I can have like unpredicted behavior, something that could bite you, basically. Something that's also strange is that doesn't always happen. It depends of the size of the underlying array. So for example, if I had an array, like if the underlying array had only size 2, like here, so I have the array that is just 2 integers, I'm getting the slice of those 2 integers. If I want to append something, it cannot append it to the underlying array because the array is full, right? So what Go will do under the scenes, without telling you, is making a copy of this array and allocate more memory to it at the end. And what will happen is I will append 8 to it. I will still get the result I expect on the slice, so I will get 1, 2, 8. But the underlying array wouldn't change. And even if I change the first element of the slice now, it's pointing to a different array. So this array is, like the first array won't be changed, as you can see at the bottom here. So I really don't recommend initializing slices like that. That could be quite tricky. Those are hard things to debug. Yeah, so slices, fun. Channels. So channels are made with make as well because they need some initialization. And channels are not much more, I'm simplifying here, but are not much more than a buffer and a lock. So channels used to communicate memory and do synchronization. We can do, if we just do make channel of integer, like the first line, we do an unbuffered channel. What that means is when you want to write for it, there's no buffer. So if you want to write for it on the channel, you need something listening at the same time. So it will, like the write will block until something reads from this channel. To go around that, if you want to have a buffer, so if you want to be able to write to it without blocking, you can do a buffered channel, which basically tells you make channel of integer with a capacity of 3, so the channel can hold 3 values until it blocks on write. And once things will be read off the bottom, you can write more to it. So yeah, that's also something to be aware of because, I mean, they look pretty similar, but they behave very differently. So be careful. Yeah, also, something I really like about channels is they're not always about sending information. Sometimes you just want to send a message. You want to say, like, you send an event, firing an event. And in that case, if the information that you send across the channel is irrelevant, you should specify this intent, like not have people checking the value and trying to do some logic around it by making a channel of an empty struct. So basically, it's a channel that will fire events, kind of, but will never, like, the value will be always empty struct inside, because that's the only thing you can send over this channel. Okay, let's touch a little bit about garbage collection. So I'm going to talk about a little bit, like just touch briefly on how garbage collection is done in Go. So it's a mark and sweep algorithm. So here we have the stack on the left and the heap on the right. And we have a pointer pointing to two pointers on 2 different frames, pointing to 2 different elements on the heap. So we can imagine the second function returned, and therefore we have just one pointing to an element on the heap. So the garbage collector will do two passes. The first one, it will do a mark, which you will go through the stack and see all the pointers we have there. And every element we have on the heap that was pointed to by the stack will be marked as accessible, basically. And then we have the sweep, which is the second pass, where you go through the heap and you remove the elements that are unreachable. So you don't, in reality, you don't really remove them, you just mark them as unreachable, and therefore like the memory can be reused. So they're not like deleted if we don't need to, but that's kind of the general idea. So, like I said, we first we mark the accessible entities on the heap, and then we mark the ones that are inaccessible as inaccessible, so we can reuse the memory later. So something quite fascinating is happening with the Go garbage collector recently. So with Go 1.5, there's been a transition from what was before stop the word garbage collection, which means that it would stop all execution, do the mark, do the sweep, and then resume execution, to kind of a hybrid garbage collection, which would do stop the word at first with bounds, so it cannot go on forever, and then continue the garbage collection in a concurrent manner, and that's kind of a step forward into concurrent garbage collection, which will allow to do stuff in Go that were not possible before. So the issue with stop the word is that basically your execution stops for a few milliseconds. That's really a problem with time-critical programs. So if you think about planes or brake systems, it would be a problem if they went offline for a few milliseconds every now and then. But once we move to a concurrent garbage collection, it will all be much better, and Go will no longer have this problem. So I really hope they will go forward. Right, so sometimes garbage collection, it can be kind of a problem, like I said earlier. So it can make your system unresponsive or a bit slow, and if you see that in your problem, it's really a problem. There's a few ways around that. Well, you can first, you have two ways around that, basically. First of all is try to create less garbage. So see if you can allocate less memory, see if you need all the pointers that you use, maybe use more local variables instead of pointers. But then your memory usage will go up, which is a different problem, so kind of find a balance. And another solution that is widely used as well is to make resource pools. So for example, if you know that one kind of struct will be used a lot, like you'll create millions of instances of it, you can create pools, like big pools, and basically instead of just forgetting about it, when you're done with it, you can specifically put it somewhere so it will still be referenced. And the next time you need an instance, you can get the one you already allocated instead of allocating a new one and waiting for the old one to be garbage collected. Now, the problem is monitoring your memory use is not always trivial. So it is, most monitoring systems will tell you how much memory the system uses or the process uses, but to find in your application where are the problems, it can be quite challenging. So I can give you a few clues on how to look for those, and what to do in those instances. So first of all, I would start with the benchmarks. So if you haven't tried it, the benchmarking tool in Go is very good. It's in the testing package. It follows kind of the same principle as testing. It's really useful to determine performance. And if you use the test benchmem tag on it, it will show you memory allocation. So it will, like, your load test will return something like that, where you would still see the speed of the execution, but you also see the bytes allocated and the number of allocations per operation. So that's really useful. If you benchmark your functions, you can keep track of how much memory you're allocating, or if you're trying to reduce the number of memory allocated, the amount of memory you're allocating, it's really useful for testing. So you can just benchmark a function, try something, run the benchmark again, see if you went up or down, and repeat. Then this is kind of a micro optimization. Some people might need that, some people might not, but I think it's quite neat. So basically, this is an old C trick to reduce the size of your structs. It's called bit packing, and that comes from the fact that in most systems, when you do data structures, your data must be aligned. So, for example, if you have an 8-byte variable in a struct, then like the struct will be kind of 8-byte aligned. And as you can see, for example, in the first struct I make, I have a Boolean that takes 1 byte, 1 bit to be more precise. You then have a float 64 that takes 8 bytes, and just an int that takes 4 bytes. And if I check the size of it, which you can do with the unsafe package, I can see it's held in 24 bytes in memory. So what happens here is like the biggest variable in the first struct is the float 64. Therefore, the struct will align on 8 bytes. So it'll be in blocks of 8 bytes. So if we look at, like, we'll have exist, that will take 1 byte. And then it will try to squeeze precise number in there, which is another 8 byte, but then we'll get 9 bytes, which is not good. So we go under, so it'll be 8 bytes, 8 bytes. So it'll be exists, 7 empty bytes, then precise number for 8 bytes, and then just an int. But again, just an int is just 4 bytes, so it'll add some padding in there, so we'll have 4 empty bytes. So what you can do is just by rearranging the structure, you can have 8 bytes at first, and then on the second line, you'd have an integer is 4 bytes and a Boolean that is 1 byte, and those hold in the second line. So as you can see, the first one takes 24 bytes in memory, and the second one takes 16 bytes, which is kind of like a huge deal in this case, like a third of the memory saved just by flipping a few arguments. But in practice, I didn't find that to save that much memory. Maybe someone had. I'm sure someone had. But it has never been the solution for me yet. I'm really waiting for that moment. And I would say I didn't put it last by accident. Use the profiler. So I have a tool called PPRO that is provided with the Go tools that lets you do amazing graphs and get really accurate reports and like even live monitoring of your system, so knowing how much you heap, how much your how much your stack is on, and I think you can really get some great results from it. As you can see, like the graph I put on the right, sorry, is it's a subgraph from what you would get from the profiler, but it will show you. This is from a memory profile, so it will show you like where the memory goes and how what lower level function it goes through, and you can see at the end there's quite a lot of stuff. It goes to sweep, so if you see this kind of stuff, you know there's a lot of garbage created, and if you go up the stack, you can kind of figure out where it happens in your code and kind of see things from there. But to be honest with you, I found it quite painful to use. It's not very straightforward to set up, but when it does, it gives you great results and a great insight into your system. Memory leaks, anyone? Yeah, so memory leaks are always fun issues. So often, when I say often, it's always comes down to zombie go routines. For example, when you do an HTTP request, you get a response back. This response has a body. If you don't close that body, you'll have a go routine running somewhere that has a pointer to this body. So this will stay on the heap. This will not get garbage collected. So if you keep doing HTTP requests, the heap will just grow and grow until you run out of memory. That happened. So yeah, you need to be aware of those. Really hard to debug, again. I think best, so if you can use a profiler, it'll give you an idea of where the memory is coming from. But really, most of the time, I only found the solutions by just looking very carefully at the code and going to it bit by bit. A lot of the time, what happens as well is you have things that look like memory leaks, but that are not actually memory leaks. So, for example, like I said, like the stacks in Go are elastic. So when you need more frames on your stack, you'll just grab them off the heap, which will increase your overall memory consumption. But when you're done with them, you'll put them back on the heap, but they will not necessarily be released to the system. So Go really likes to hold on to resources in case it needs them later. So you can see, for example, if you're running a web server, you get a lot of requests, and you get a lot of new Go routines, and you get a lot of new stack frames. So your memory consumptions go up. And then your traffic goes down, but your memory consumption stays up. And that might look like a memory leak, but it's really not. It's just Go that's holding on to resources for you to, in case it needs to claim them again. And eventually it will go down or not. It really depends. Something that I find also is when you're doing very garbage intensive processes. So when you're generating a lot of garbage and you have like the garbage collector working very hard, sometimes it kind of just doesn't keep up with the amount of garbage you produce. In that case, you can just force running garbage collection in your code just to try it out, just to see if that's really the problem. If your memory consumption goes up just because the garbage collection hasn't run yet, or if you really had a memory leak. So, yeah. I hope I give you a few interesting things to think about. I'll be taking some questions. Yes?
Your last slide, you said poor runtime, sorry. So your last slide, you recommended calling runtime GC. I would suggest never doing that, in fact, because it does a stop-the-world collection. It'll be slower than letting the garbage collector do what it ordinarily does.
Right. No, what I was saying here is if you want to try it out and see if that's really the case, like if the problem is, if you're testing a program, I'm not recommending doing that on production. Definitely not. But like if you're trying out a program and you see that your memory consumption goes up and you're not sure if it's because you have a memory leak, it's because of something else, or if it's because just the garbage collection hasn't run yet, you can force it by code just to make sure like it's not a garbage collection issue.
I see, okay. Earlier on, you also mentioned that new did a heap allocation of the variable. And in fact, that's not necessarily the case. You can use var x type, or you can use new type, and they're essentially identical. Whether or not they are on the heap or the stack is up to the compiler.
Right. So new will return a pointer, and like when you get an address, the address it points at is always on the heap. So maybe on set. Right. Yeah. So if it's on set, yes. So yes. Oh, wait.
Okay, I'll talk quieter. With the bit packing point you made earlier,
yes.
That seems like an obvious optimization if you knew about it. Is there a reason that can't be optimized automatically at compile time?
Well, honestly, I don't know. I think it can be. I think, but we'll have to.
I can take that if you like. So there's a couple of reasons why
Sure.
A compiler could do that. But one reason is that in the interface with C programs, it's useful to actually be able to predict the memory layout. The second is that in a concurrent program, the cache line in which the variable lives is important, because it might be that two CPUs are fighting over the same cache line, and being able to put them in, being able to have control that is not just about minimizing the size of the struct may be more valuable.
Thank you. Anyone else? Thank you.
Thank you very much.